Hello, everyone, and welcome to our webinar for this afternoon with the eminent scholar, Dr. Mike Goodchild, as our presenter. We're going to be hearing the topic of reimagining the history of GIS. As a reminder for logistics, your microphones are going to remain muted throughout the presentation. If you have questions for Dr. Goodchild, please type them out into the question space, and there will be time for us to address those at the end. If you have any technical issues, you can send me this is Diana Sinton. I didn't introduce myself. I'm Diana Sinton. I'm the Executive Director of UCGIS, and I'm going to be the host for this afternoon's webinar. If you have technical questions, which I may or may not be able to troubleshoot, but I'll give it a go, type into the chat space, and I'll be able to monitor that to the best of my ability and see if we can figure out what your audio issues might be. As a reminder, this session is going to be recorded, and following the webinar today, we'll be sending out the link to all registrants and also to the broader UCGIS community. So it's about a minute after. People will continue to join us, but Mike, at this point, I am going to turn it over to you, and thank you very much for sharing this presentation with us today.
Very good. Do you have my screen? No.
Not quite yet.
Yes. Where's Mike? There we go. How's that?
Yes, now we do.
Great. Okay, so good afternoon and welcome. And I'd like to say just a few things before this to cover my own motivation, why I'm doing this, why I think this is an interesting topic. And it comes about from various origins. One is that when you retire, and I've now been in the GIS field for upwards of 50 years, when you retire, you do have an opportunity to look back and wonder, in this case, whether things might have been different. And this is, I think, one way of thinking outside the box, and it's kind of a useful way. And I think if you follow me today, you'll maybe agree with me at the end that there are many opportunities that we've not necessarily followed up on, because in many ways we've been constrained by history as it has developed. I'm also interested in this topic. This is going to, it's not clear from the title, but this is going to move into the area of discrete global grids, which is a topic I've been interested in for quite a while now, maybe 25 years. And I've always been interested in trying to promote it more because I think it's a very interesting and very powerful topic. And one thing at the end of today's talk is that I'm going to introduce a motivation for this, which is not the usual motivation, but I think is a very powerful motivation. And then another origin is a legal case I got involved in a couple of years ago when Google was being sued for patent infringement. And as a result, I got to look into Google Earth in great detail. In fact, I got to review the entire 12 million lines of code of Google Earth. And so I found out a lot about what's really going on in there, and that will feature in this talk as well. So without any more ado, here's a point of departure, which I think is a useful point of departure, and that's spatial analysis, or as we should be saying these days, spatial analytics. And this is, of course, a body of techniques developed over the past 70 or more years with various objectives to make discoveries from geographic information, to find optimal locations for things, to reveal and explain what might otherwise be hidden in geographic data, to predict where events are likely to occur and when. All of these are possible motivations for spatial analysis. And I'm particularly interested in this talk in the role of technology in the development of spatial analytics or spatial analysis. So here's a proposition. When a technique of spatial analysis is invented or tested and implemented, it tends to reflect the state of technology at the time. And if we're going to think about GIS as evolving over 50 years, then that state at the time is the state of technology at the time that GIS was invented, which takes us back to the 1960s. And if you accept that point, then note also, of course, that technology has been advancing rapidly for the past 70 plus years. It's advancing now even more rapidly than it has in the past. And so this immediately begs the question, would the technique have been updated, and would the legacy of earlier technologies still be with us? In other words, has GIS, arguably invented 50 years ago, been updated to keep up with technology as it has evolved? Or are we to some extent constrained by the legacy of those earlier technologies? And that's the question I want to explore this afternoon. And just to begin, let's take a very well-known example from statistics and basically ask the same kind of question. So let's take least squares regression. Least squares regression was developed long before computing. There were no computers at the time that least squares regression was developed. And in order to calculate, or in order to estimate the parameters of a simple linear relationship, it was necessary to use algebra rather than computation. And a choice was made to minimize squared deviation. We minimize the sum of squares of residuals. And a great advantage of doing that is that in order to minimize squared deviation, if you differentiate the squared deviation with respect to the parameters, that gives you an algebraic solution, a very simple analytic solution to the problem. So we have equations which allow us to compute the slope and the intercept of the linear relationship. So you could argue that the choice to minimize squared deviation was dictated by the need to come up with an analytic solution. And certainly any other minimizing, for example, the absolute deviations, sum of absolute deviations, or the sum of cube deviations would not have led to an analytic solution in the same way. So was that choice a choice dictated by the technology of the time? And if it still survives, are we still to some extent constrained by the legacy of that earlier decision? So are there other examples that are to some extent legacies of earlier technological context? And you might therefore ask, these days, least squares regression, of course, is one of many, many techniques for fitting a line, and many of them are purely computational because analytic solutions could not be obtained in simple form. So you might argue then that the growth of computational statistics in the last few years is a response to changing technological context. The technology of today gives you much more freedom in how to do simple things in statistics. And so let's take that basic argument and go to GIS. And many people, me included, would argue that the origins of GIS go back to the work of Roger Tomlinson in the mid-1960s, working for the Canadian government and working in conjunction with IBM. And I got to know this system very well in about 1972, when one of my grad students moved to Ottawa and encountered the system and started thinking about how it might be used in various kinds of environmental applications. So this was the Canada Geographic Information System. It was developed to handle the data that had been collected by the Canada Land Inventory, or CLI. And Roger's brilliance, I think, was to see that if you took those maps and put them in a computer, the task of calculating areas would become straightforward. It was areas that were promised by the people who initiated this project. They promised the Canadian provinces and the federal government that they could obtain statistics on the use of land across Canada. And that, of course, comes down to a simple problem of computing the areas of polygons on a map. And if you think about it, to do that by hand is extremely tedious and extremely inaccurate. So doing it by computer made a lot of sense. So this is in the context, of course, of computing in 1965. And if you're as old as I am, you may have recognized over here the front panel of an IBM 360/65 at that time. So computing in 1965, an IBM 360/65, much less CPU than your smartphone, only a few kilobytes of main memory, little hard disk, and almost all of the data storage had to be on sequential tape. So, interesting question. How do you take the contents of a whole lot of maps, and there were about 50,000 source maps in this project, how do you take those and express them in digital form on sequential tape? And in order to do that, various design decisions had to be made. So the first, and to some degree the most important, was to treat the source maps as the truth. So the question of whether the source maps were in fact an accurate representation of the real world was never considered. That is, of course, what we would today recognize as uncertainty, and uncertainty was never a significant part of this project. The decision was made to scan the maps using a raster scanner. At that time, 1965, no raster scanner existed, but IBM built one from scratch, large enough to handle maps, and to take the results of the raster scan and vectorize them, because in vector form, the possibility was for massive compression, and of course to analyze the data in vector form. And the data model that was developed is what we today might call Esri's coverage model, or an ARC node data model. And this was, I think, again, a brilliant solution by IBM to represent the maps in that way. So here's an example of the kind of map we're dealing with. This is part of Quebec, and it's been classified according to the soil capability for forestry, which is one of the 7 layers in the Canada Geographic Information System. And class 1 is the best land, and class 7 is the poorest. And here's this is not actually from CLI, but is a typical of the kind of data we're dealing with. This is actually part of Afghanistan. And you can see that the area has been subdivided into polygons of different class. And that's basically the type of data that this first GIS was built to handle. So here's the ArcNode data model. And as I said, I think this is a really brilliant decision on the part of the people at the time. You've got 4 polygons on this map, and instead of treating the polygon as the basic element, the decision was made to treat the common boundary between 2 polygons as the basic element. So instead of 4 polygons, we've got 9 common boundaries between pairs of polygons, and of course, including the 4 boundaries that form the outer boundary of the map. And this is, I think, non-intuitive, and yet it turns out to have enormous advantages in the actual algorithms which had to be built. For example, you can compute the areas of all polygons by making a single pass through the arcs, through the common boundaries between polygons. And that's a very useful thing if what you're doing is processing a tape, and the tape has the arcs laid out sequentially. I'm using the word arc here, and historically that's quite significant because it's the reason ArcInfo was given the name it was, and the reason that ARC still survives in many of Esri's products, because they essentially adopted this structure. So with those 9 arcs, we record a table in which we have the from node and the to node, and the left polygon and the right polygon for each of these arcs. And that was the basic structure, and it's the structure that survives today in Esri's coverage data model and various other places in the GIS field. So 50 years of progress, some brilliant decisions made in 1965, followed by 50 years of trying to catch up or taking advantage of new technology. So hard drives replaced the tape, massive increases in speed and in main memory. The data model. The first way to approach this would be to say, I've got different types of data beyond what the Canada Land Inventory was dealing with. They're not polygons that exhaust the plane. For example, I've got roads. How do I deal with roads in this data model? And the answer, treat them as arcs, allow them to cross without intersecting, and allow them to dead end. In other words, you extend the data model to include a new type of data. But eventually, that became dead weight. And so by the 1990s, the coverage model had essentially been replaced with a concept of flexible topology, and that's what we see today. Yet, the coverage model, in fact, still survives, and you can still compute with it. And perhaps more importantly, the map is still the truth. And by and large, I would argue in the GIS field, we've made little real progress in handling uncertainty. We've got a huge literature now on uncertainty, lots and lots of books and papers, but little real progress in modifying our GIS technology to handle uncertainty. And because we regarded the map as the truth in CGIS, that was a projected Earth. And by and large, we are still flattening the Earth in much of what we do in GIS. The layer is still a central concept, and these days we still integrate data into horizontal layers, whether you're talking about Google Maps or ArcGIS or whatever technology you like to think about. That maintains the conceptual link to maps, which I think is tremendously important because it means you can, in your elevator speech, say that GIS is a container of maps, and that makes a lot of sense to people. However, we could slice the cube of data. If you think of data as a 3D cube with time on the vertical axis, or if you think about it as a 4D hypercube, then we could slice it on any dimension. The layer approach basically slices it horizontally, but we could slice it vertically, and we could slice it in any direction. And so this use of the concept of layer is to some extent a legacy of previous technology, leading to the question, are there opportunities we've missed because we've not chosen to slice the data cube or the data hypercube in other directions? One very major issue, though, here is the question of maps versus globes. And back in 1965, this was a very simple choice because maps are easy to print, they're easy to store, they're easy to ship. You can make them at any scale. Globes, on the other hand, have a fixed scale. They're hard to print, they're hard to store, they're hard to ship. However, and today, of course, if we thought about digital globes, we'd recognize that digital globes are just as easy to store and ship as physical globes, as digital technology. And digital globes certainly were never even imagined in 1965. So in 1965, Tomlinson's choice was the right one. But is it still the right one? And of course, that's the central question here. So are we still right in treating GIS as a container of maps rather than a container of globes? So here's a globe. Of course, this is the kind of globe that you sometimes used to find in the middle of dance halls, and they would reflect light in different directions. And the idea of a digital globe really has gone through two different generations of solutions, and I want to talk about those. These, of course, date from the late 1980s, the early 1990s, so they're a quarter of a century after Roger Tomlinson's choice. But they do allow us to visit this question, is that choice still the right choice? So one consists of warping a 2D image to a 3D surface, and the other consists of taking a platonic solid and dividing it hierarchically. And I want to talk briefly about both of those. The first one came first, and the second one came later. But both of them represent solutions to this question of building a GIS as a collection of globes rather than a collection of maps. So warping an image. What does this mean? Well, in the late 1980s, Silicon Graphics, IBM, and various other companies developed workstations, graphics workstations, which were capable of warping a two-dimensional image onto a three-dimensional solid. They used OpenGL as a software library, and the graphics processing units had advanced to the point where this was technically feasible. Now, it was technically feasible, but these boxes would still have cost you serious six figures. $250,000 was not unreasonable at that time. These were expensive solutions. They weren't widespread. Nevertheless, it was possible at that time then to imagine taking a two-dimensional image and warping it onto a globe. And many people immediately saw that possibility. And so we started to see a run of technologies in the early 1990s that did just that. They created a digital globe by warping a 2D image onto a curved surface. Many of them use the plat carré projection. Plat carré is not necessarily the commonest term for this, but what I'm talking about is sometimes known as the unprojected projection or the geographical projection. And basically it consists of flattening the Earth so that you have latitude on the y-axis and longitude on the x-axis. Plat carré from the French meaning simply a squared plate. And many of the solutions built a multi-scale image using a quadri, and that allowed them to rapidly pan and zoom over the Earth. The other problem you have when you try to build a system like this is that there are 10 to the 12th square meters, 5 times 10 to the 12th square meters on the Earth's surface. It was and still is pretty much impossible to store fine resolution data for the entire Earth. So they developed systems for retrieving tiles of data from spatially distributed servers. So imagine something like this. Here's part of the eastern seaboard, New Jersey, Delaware, Maryland. And we're looking at a quad tree laid out on that flattened Earth and looking at tiles in the quad tree. And so if you go down, if we took, for example, this resolution here of the entire map and pulled out one of the small pieces, you would see it at the resolution of the entire map, which is pretty coarse, and you would not be able to see many of the features that you were looking at. But if we regarded that small piece as a separate tile and used a resolution which created the same volume of data in that tile as we have for the entire larger tile, then you would get finer resolution. And so at this point, you'd be able to see and recognize Wilmington, Delaware, and Brandywine Creek, and many other features in that part of the world. So this is the basic idea. You create a quad tree of tiles, you store those tiles on the server, and you pull them back as needed. And that's, of course, the principle on which Google Earth operates and many of the other digital globes. So here's actually the first demonstration of this possibility, the first public demonstration. This is 1995. It's a German company called Art+Com, and it's demonstrating its technology at SIGGRAPH 95. And you're looking at Japan and the Korean Peninsula, and the operator is able to zoom down, pulling tiles of greater and greater detail from a central server and displaying them on the screen. And that rather fascinating large ball that's adjacent to the operator's left hand is actually a kind of mouse, which if you spin it, you will spin the globe on the screen. So you've got the ability to pan and zoom over the Earth and zoom down to fine detail. In the case of this demonstration, going down to fine detail about, for example, Tokyo or Mount Fuji. And doing it with relief. So the image is draped over a digital elevation model. And so you've got, in fact, something very much like Google Earth turned out to be when it was released in 2005. Small company, Keyhole startup, developed something called Earth Viewer. And the significance here is that by the time it was launched in 2001, the GPU in an average production laptop was sufficiently sophisticated to do this. You no longer needed the six-figure graphics workstation. You could do this on virtually any production GPU, any production laptop. Several technical advances were made by the time Google Keyhole came out. It was not necessary to retrieve every possible tile because you could scan a tree of metadata to identify the tiles you needed. Various tricks were used to prioritize the fetching of tiles, and this essentially then is what Google acquired in 2004 and launched in 2005 as Google Earth. So this essentially is the first digital Earth. So let's go now to the second topic, which is actually subdividing the globe into something like a grid. And the problem here, of course, is that you cannot lay a raster on a curved surface without distorting the sizes of the raster cells. It's impossible to tile a curved surface with squares. You can't cover the Earth with squares. And so because of that, Google Earth still uses the flattened Earth approach, which was the first approach that I've covered. However, a much more sophisticated and much more elegant solution is available in the form of what's called a discrete global grid. And there are 5 possible starting points here, the 5 platonic solids. So you can build a solid using 4 identical triangles, that's a tetrahedron, 6 identical squares, gives you a cube, 8 triangles, 12 pentagons, or 20 triangles. And all of these, with 2 exceptions, the tetrahedron and the dodecahedron, have been the basis for extensive research and experimentation in what's become known as discrete global grids. So a DGG is one of these systems created by taking a platonic solid and subdividing its faces into smaller and smaller and smaller pieces on a hierarchical basis. DGG is now the subject of a specification from OGC. OGC has published a spec for DGGs, so they're becoming much more common than they used to be. Here are the 5 platonic solids, and as I say, the 2 that I'm not aware that anybody has actually explored are the tetrahedron and the dodecahedron. Here's the one that I've done most work with. This was developed by Jeff Dutton in the 1990s, and he gave it the name of a quaternary triangular mesh, and it's an octahedron-based DGG. So you can see the 8 faces of the octahedron, which are spherical triangles, and then they're subdivided on the basis of a rule of 4 by connecting the midpoints of the sides. And this implementation, you'll notice that it doesn't use great circle arcs, except at the top level. It uses instead linear functions of latitude and longitude. So you can see that they're all triangles, but the triangles vary quite significantly. In the corners of the top level, the octahedron, the triangles are approximately right-angled, and in the center of each of these faces, they're approximately equilateral. So there's quite a bit of variation. No variation, though, in topology, except if you consider the neighbors, and about a 10% variation in area in this particular scheme. Here's another one. This is GeoFusion, developed by Paul Hansen at Santa Cruz. And it was acquired by Esri, became the basis of ArcGlobe, and also, incidentally, is the scheme that's used by British Airways in their cabin displays of the progress of an airplane. This is based on the cube, and again, it's subdivided into triangles. One variation, though, he decided that the polar faces, the top face and the bottom face, would be replaced by 4 triangles. So there are actually 12 top-level elements in this scheme instead of 6. But basically, you divide the world into tiles, and then when you fill the tiles, you have a digital globe. And because it's hierarchical, you can zoom down to any level of resolution you like. This one, perhaps the most elegant. This is based on the icosahedron, so 20 triangles. And it's arranged so that the hexagons are of exactly equal area. This is truly an equal area projection. The sacrifice you make, of course, is that they're not exactly of the same shape. And because they're hexagons, they don't nest except at every other level. So you have to go 2 levels up or 2 levels down to make the hexagons nest inside each other. This is an illustration from the work of a company called Pyxis Innovation, Pyxis, and they've developed some very nice products based on this scheme that let you do all sorts of things that, of course, a regular GIS will also let you do. So, obvious advantages to a DGG. No hiatus at 180 longitude. So there's no break. You go smoothly over 180 degrees longitude. You go smoothly over the poles. Approximately uniform area and shape. And there's been a fair amount of work done on various metrics to compare the alternative DGGs. And of course, how uniform the areas are and how uniform the shapes are becomes one of the metrics. Approximately uniform topology and hierarchical subdivision. So with QTM, level 0, that's the 8 faces of the octahedron, each one about 500 million square kilometers. Go down to level 9, and you've got triangles of about 1,000 square kilometers each. More advantages. Spatial resolution in these schemes is always explicit. Unlike vector data, triangles are primitive elements, which is well suited to rendering in GPUs because GPUs typically use the triangle as the basic element. No need to flatten the Earth, none of the distortions that result from flattening the Earth. And there are others, and I mentioned a couple more in the paper having to do with modeling over the surface of the Earth. There are many, many advantages to these kinds of schemes. I thought at this point I'd just introduce a couple of examples of the kind of pickle we get into when we insist on flattening the Earth. And the point here is not so much that we shouldn't flatten the Earth at all, but that we shouldn't flatten the Earth in order to create a database. Because when you flatten the Earth before you create the database, then the distortions of the flattening get inherited by everything you do with that database. And these illustrations, I think, will make that point. I'll come back to this in a moment after I've gone through these. So here's number 1. This is a very famous example. It comes from The Economist magazine in 2003. It's been reprinted many times. One doesn't want to pick on The Economist, but the point here is that this same mistake has been made many, many times. Nick Chrisman has collected a whole mass of examples of this fallacy, basically. So this is accompanying a story about North Korea's missile threat. These are concentric circles centered on Pyongyang. Purportedly 10,000 kilometers is the blue circle and 15,000 kilometers is the red circle. Now, if you're familiar with the history of the meter, you would immediately recognize that this is wrong because that blue circle with a radius of 10,000 kilometers, the French defined the original definition of the meter was 1/10,000,000th of the distance between the equator and the pole. In other words, from, let's say, approximately Singapore, or where this map is labeled as Indonesia, all the way up to the top of the map is 10,000 kilometers. And clearly the 10,000 kilometers here is much too small. This is also notably a Mercator projection. And on the Mercator projection, the pole is at infinity. So we don't even get to the top of the map in 10,000 kilometers. About 2 weeks later, after various people have pointed this out, they published the correction. And this is where you can really get to. In other words, of course, the fallacy is to draw concentric circles on a flattened Earth and assume they represent equal distances, which of course they don't. So instead of being barely able to get to the Aleutians, you can get almost to Milwaukee. Here's another one which bothers me much more, in fact, because it's much more common. And that's here. This is a typical kind of product you see from Earth system science. This is global sea surface temperature. And you won't be able to see this, but in the top left of the image, it says 50-kilometer global analysis. And the problem here is that, of course, across the equator, if you draw a horizontal line across the equator, you've got about 800 50-kilometer pixels. If you do the same at the top, the entire top of this map is 1 point. It's the North Pole. And the entire bottom of this map is, again, 1 point. This is a Platte-Carré projection. And even if you come 1 cell width out from the North Pole, in other words, 50 kilometers from the North Pole, instead of 800 data points, you've only got 6 at 50-kilometer resolution. So it's really misleading to claim that this is 50-kilometer global analysis. This is 50-kilometer at the equator and nowhere else. In all cells, of course, are 50 kilometers north-south, but only at the equator are they 50 kilometers east-west. So pixels at the equator, 50 kilometers by 50 kilometers, pixels at 85 degrees north, 50 kilometers north-south by only 4.4 kilometers east-west. And by the time you get to the pole, the base of each pixel is essentially a triangle, and its base is only about somewhat in excess of 500 meters. Here's another one, mostly for entertainment purposes. This is, again, Platte-Carré, and this is the map that's displayed in the cabin of Emirates Airlines, at least it was last time I flew Emirates. And so I'm going to use the example of flying from Dubai in the Gulf, the Emirates Airlines hub, to the west coast of the US. Because when you do that, the route that you follow starts out by going north. And it goes north over Iran, Tehran, over the Caspian Sea, over the Ural Mountains, and almost exactly over the pole. And so if you're sitting watching this in the cabin, as I've done, and it's a 16-hour flight, so you really got to be awake 8 hours into the flight to see this happen. But it's really exciting when it does, so it's worth staying awake. Because at a point in the flight, suddenly, the plane will appear to turn a right angle to the left and to fly across the top of the map at infinite speed and then execute another right angle, turn to the left. Now, of course, it hasn't done that at all. It's simply flown smoothly over the pole. And if we had a digital globe instead of a digital map, you would see nothing unusual. But because we're using a Platte-Carré projection, what you see is a hugely distorted view of what's actually happened. And notice that because you're flying very close to the North Pole, it's a matter of chance as to whether you turn right or turn left when you get there. So I want to talk about what I think of as a new motivation, and this will just take the last few minutes of the talk. And this is about data integration. So this is nothing about globes versus maps. It's simply about integrating data. And the basis for this is, if you think of a simple example, suppose you went to your city hall, and your city hall has how many layers of data? Maybe 100, no, much more than that likely. And some of them are raster layers, and some are points, and some are areas. And you ask them, tell me everything you know about a single point. And let's say it's the location of your house. What do you know about my house? Then you think through what would have to happen in order to do that in conventional GIS, because the GIS is organized as a series of layers. And so in order to answer your question, it would be necessary to overlay all of these layers. And depending on which layers we're talking about, those overlays can be quite slow. So the fact is, it would take quite a long time to answer a simple question like, tell me everything you know about this point. And the paradox here is that even though we've presented GIS as the technology for data integration, In fact, integrating data can be quite difficult because we chose to organize data layer by layer. So here's the question: what if all data were expressed on the same set of spatial features instead of some raster, some points, some areas? And what if they were hierarchically nested to accommodate different scales and resolutions? There would then be no what we call spatial mismatch, no on-the-fly resampling, and no need to do spatial joins. It would all become very simple. So here's a couple of examples. Here's an analysis of, on the vertical axis, median value of house, and the horizontal axis, percent black for the counties of Mississippi. And you're looking at what's clearly a negative relationship. The higher the percent black, the lower the median value of house. This is census data from 1990. It comes from a single table, 2 columns of that table. And so it's not a GIS analysis at all. It's simply something that you can do in Excel. Because both data sets, both variables are expressed on the same set of geographic features, the county. Here, on the other hand, Santa Barbara County, and asking a simple question: what's the relationship between vegetation cover type and elevation? Elevation is by raster points. It's a digital elevation model. And vegetation cover type is by polygon. And in order to answer this question, I have to do a spatial join between a raster data set and a polygon data set. That takes time. And if I've got multiple variables, it takes multiple time. Here's an example of spatial mismatch. It's a term you come across quite a lot in social applications of GIS. This is part of Austin, Texas. And the red lines are the boundaries of elementary school districts, and the other lines are block groups. And highlighted in green are the block groups which are cut by the boundaries of the school districts. So in order to do this analysis, again, it's necessary to overlay the 2 data sets, do a topological overlay, in order to find out how much of each block group lies in which school district. So what I'm looking for, what I'm suggesting here, is this notion of congruent geography, using the same set of spatial units for every variable. And we have in GIS a lot of literature, a lot of experience with using, for example, congruent rasters. Many raster-based systems simply assume that every layer has the same geometrical basis. Dana Tomlin's cartographic modeling was based on this same principle. And yet, of course, this requires flattening the Earth because it's rasters, and there's no universal standard, and it's a single level of resolution. The U.S. Department of Agriculture promotes what it calls I'm too ahead here. Integrated terrain units, the idea that you subdivide the landscape so that each piece is uniform on all characteristics. The multipurpose cadastre, the notion that the parcel is at the root of everything. You use the parcel as the congruent geography. And then finally, common land units, which is the U.S. Department of Agriculture's idea, where the basic unit is a field and everything else is based on that. The point being that if we could agree on a congruent geography, then data integration would be trivial. And so that's, of course, exactly what you have with a discrete global grid. And you've got a major advantage that the geography can be at different scales, different levels of resolution, and that the various levels of resolution nest within each other. So just to wrap this up, and then we can go for some conversation. Discrete global grids can provide a congruent geography for the planet. The greatest value of discrete global grids could be in data integration then, rather than in digital globes versus digital maps. This is a little bit of a tongue-in-cheek fantasy here, but the Meridian Convention, which was brought together in the late 19th century and agreed on the Greenwich Meridian as the zero of longitude, is it time for a new one? Would it be possible to agree on a universal standard that could be used as a congruent geography for all of our activities? And now to come back to the main point then, to what extent are we subconsciously limited by earlier technologies? The phrase horseless carriage was the way people found to talk about the car, the automobile, in the early days, because it was easiest to think about it as a prior technology, the carriage, simply without a horse. The stack of maps or layers, as the metaphor for GIS, I've argued, is very limiting, and it's related to prior technology. So can we find other examples? To what extent is today's analysis limited by the legacy of past technologies? I talked about variance and standard deviation, least squares, regression. We can also talk about parametric tests, the F-test and the T-test. We can talk about the habit of aggregating data into things like census tracts or counties. And we can talk about limiting study areas because making them bigger would simply create too much data. So there are many, many examples, I think, of where the limitations of past technologies still live with us and limit our thinking. So thanks very much for your attention. I hope that was interesting, and I look forward to a few minutes of discussion.
Mike, thank you very much for that. Indeed, there are a lot of ideas that this comes up that brings to mind. I'd like to mention again to the participants, if you have a question for Mike, please type it into your chat space. We might try to turn some microphones on, but first I want to make sure that we get things recorded in the question space too. And as people are doing that, Mike, I'm wondering if you could reflect on this or give us your comments on this. Some of the things that you've described here are in some ways aspirational for the future of GI science. Where do you see some of these research activities taking place? Do you see these things happening in universities right now? Do you see them, a lot of the activity happening in industry or with commercial GIS groups? And as part of that, I'm thinking about with some of these things that NSF might fund. Do you see some of these basic research in these areas fundable by NSF, and what kind of directorates at NSF are interested in these questions?
Always a very interesting question, and I think from my own experience, I've spent a lot of the last 50 years, or at least 30 years of that, trying to nudge industry to move in a direction which is more in line with the basic needs of science. I thought it was tremendously exciting around 1980 when commercial industry started coming up with software that was engineered to industrial standards and yet could be used in our labs. And ever since then, I've been trying to push for more and more of an approach or a perspective which is more consistent with the needs of science. And the uncertainty agenda is very much part of that. It's always been very frustrating to try to persuade industry to take uncertainty seriously. Their answer, of course, is very simple. Our customers don't want it. But from a scientific perspective, if you think about this technology as being useful for science, then it's absolutely essential. And there are many, many other examples like that, I think. If you look for industry which is specifically geared to the needs of science, it's very hard to find. You can think of examples in the statistical world where the market for stats software in the scientific community is large enough to support a serious commercial activity, but that really doesn't seem to be true in the GIS case. So the relationship with industry is always very interesting. So the point I've been making is essentially that we in academia have needs which are hard for industry to satisfy because they're oriented towards a commercial market. Another side of the question is to what extent we should simply wait for industry to invent the things that we would like to happen, such as this. But I've been through many rounds of watching startup companies get excited about discrete global grids and simply fail in the marketplace or fail to find venture capital. So I'm very optimistic about the role that the academic community has to play, not just in reflecting on what's happening, but also in actually leading what's going on. And as you know, this was a big part of the discussion over the Geospatial Software Institute possibility that we had a couple of weeks ago.
Right. Yeah, so much to follow up with right there. But thanks for those ideas. I want to make sure we address some of these other comments that some participants have put out. Do you have thoughts about Google Earth Engine, about that as a global tool?
Yeah, it's essentially separate from what I've been talking about from Google Earth and Google Maps. And its emphasis has been on providing data and some tools which are capable of working with those data. The problem that many people in the scientific community report is the lack of provenance on the data that is available and the difficulties of introducing your own data. So yes, I think many many scientists are very excited about and make very good use of it, but it's, I think, nevertheless limited. And I think the prospects of developing open source solutions or solutions that have been developed by other research groups are actually have more potential.
Okay. A question from a listener here, wondering, and I'm going to make sure I'm going to read this because I don't want to misstate things here, but do you have thoughts on the way that prior technologies may have limited the precision and or the portrayal of uncertainty in geospatial models, and how the rapid progress in computing technologies might overcome these limits in the future?
Yeah, I think the whole uncertainty question is really challenging, having thought a great deal about it over the years. It's not at all easy to represent uncertainty in a geospatial database, and certainly not at all easy if we're dealing with rasters, dealing with vectors rather than rasters. I've argued that in fact, if we were serious about uncertainty, we would never do anything with vectors. It's impossible, for example, to retrofit uncertainty onto a vector representation. It's impossible to visualize uncertainty effectively with a vector representation. So the entire field of uncertainty inevitably leads you in a raster direction rather than a vector direction. That's, of course, partly behind this notion of discrete global grids. One, I think there's, as I say, a great deal of resistance to dealing with uncertainty from the user community, because it's simply not. It's essentially a negative message that there's uncertainty in your data. And I am, I think, extremely worried about the growth of data science and what that says for our field. Because one inescapable fact about geospatial data is that there's no such thing as a piece of geospatial data that's completely free of uncertainty. Everything is subject to uncertainty. It's impossible to measure position on the Earth's surface without some level of uncertainty. And it's impossible to characterize any land use, for example, without uncertainty in the basic definitions of land use classes. And one direction that leads us in, which I personally think is very scary, is the whole question of reproducibility and replicability. We know, for example, that the kinds of maps that I was showing you, the maps that were the basis of the Canada Land Inventory, are not replicable. That two people charged with mapping the same area, even if they were experts, would not produce the same map. That's inescapable. And what does that say about replicability in our field? Replicability has been a major issue recently in some fields like psychology, where it's a matter of the question of whether experiments can be replicated. But I think we really need a very serious consideration of what replicability means for GIS.
You mentioned there the fear is connected with the growth of data science, perhaps in general. Is it that you feel that the data science community, as it's collectively referred to and how they're calling themselves that, is not aware of this, or just isn't engaging with people?
Well, I think it is one of the features that makes spatial special, right? I mean, when I say that geospatial data is never perfect, never free of uncertainty, I'd have to think hard to decide whether I could make the same claim of other types of data. But because it's a concern of ours, I think it really does need attention. I think the problem that I'm talking about essentially is that if you begin with the data and don't think about the relationship between the data and the real world, then the conclusions you reach will be conclusions about the data and not about the real world. And the only way of addressing that in our current technology is in the user's head, because we have no ways of addressing that in the technology itself. So our technology is not capable of telling us, when we look at a database, it's not capable of telling us what's missing. What is true about the real world that this database is not telling me? That's not something that we can do. And so the only place it can exist is in the head of the user. You know the expression, the map is not the territory, meaning that a map is never equal to the real world. And if that's true, then what we learn by analyzing data is a whole lot about the data, but not necessarily much about the real world that the data supposedly represents. Where can we go with that in the future? Well, a lot of things that are happening that are would be lead us to optimism. One is that we can go to finer and finer resolution. We can go to more and more data. And so we can get closer to the real world, even though we can't replicate the real world. So that's a positive. It also, though, requires us to think outside the box. And that's, of course, what I was talking about. This habit of aggregating to coarse aggregation or of studying small areas means that we miss things that are true only of fine data or true only of the interactions between small areas. And so, again, optimism because we can now, for example, analyze the entire US instead of having to cut it up into pieces. But at the same time, it's a rule of diminishing returns. You can never get to perfection. You can never get to the point where the database is exactly the real world.
Right. Excellent stop point right now where we can come to a break. I want to thank you again, Mike, for all of your time and comments and reflections here. I know there are a number of questions that we haven't been able to answer, as is the practice with other UCGIS webinars. We will, I'll share these questions with Professor Goodchild, and if we're able to get some thoughts from him back on those, then I'll share them out again with the registrants for this webinar. So I want to thank you very much again, Mike. You've given a lot of us ideas for things we might be working on with proposals in the future, and it's always great to talk with you.
And let me just say that I'm happy for anyone to send me anything by email, and my email address is not hard to find.
Right. Hey, and also that reminds me, you also at the beginning, we had a number of these thoughts you have put together into an article that has just been published this winter.
Right.
So that was, can you share that citation again?
Let's see. Yeah, the same title, and the journal is Annals of GIS. which is a Taylor and Francis journal, edited by Hui Lin, and many of you will have access to it through libraries.
Right.
Or if you don't, send me an email.
Right, and I'll include the full citation in the note
Great.
to everyone who came to the webinar today, all the registrants.
Cool.
So it's 5 o'clock somewhere in the world, everyone. Thanks again for joining us, and we will be in touch again soon. And thank all of you. This was a members-only UCGIS webinar. Very much thank you and your institution for the support that you provide to UCGIS, and we look forward to future conversations like this going forward.
Great.
Thanks,
Great.
everyone.
Thank you. Thanks.